Today we're going to finish up Chapter 16, Section 2, our discussion on light and matter. If you look at the bell ringer, what's the complementary color of blue? Well, what we're looking for is, what is something that, when added to blue, makes white light? Well, in order to get white, you need blue, red, and green. So if you add red and green, which is yellow, you would have yourself the complementary color of blue. For cyan, well, cyan is made up of green and blue. So the complementary to cyan would be the other one, which would be red. Let's look at our problem, or our objectives. Explain the cause and give examples of interference in thin films, and then describe methods of producing light. So here we go. Last part of section 16.2, formation of colors in thin films. You should have seen colors in thin films just walking around in the real world. You'll notice if you look at gasoline that's spilled on the floor or on some water, you might see a spectrum of colors. If you see oil on water, you might see a spectrum of colors. If you've looked through soap bubbles, you'll see a spectrum of colors. These are all colors formed because of thin films. So colors in soap bubbles or oil on water, this is what we're talking about here. And these all occur because of constructive and destructive interference of light waves. And this is called thin film interference because it's wave interference, obviously, on thin films. So here's kind of how this happens. I'm going to explain the writing on the right with this diagram. Imagine you're looking at a film of soap. And we know gravity causes the soap to get thicker on the bottom, more thicker on the bottom than it is on the top. If you can imagine a beam of light hitting this thin film of soap, well, this could do one of two things. It could reflect, or it could be transmitted. And when it gets here, it could reflect off of that guy and then continue out, and so on. So some would actually go through, and some would be reflected back and come through the other side of the film. So why do you see different colors? Well, weight causes the film to be thicker at the bottom. We know that. If the thickness is exactly 1/4 of a wavelength, then the round trip would be 1/2 of a wavelength, and that would produce constructive interference. Now, some people might think, well, how come if it's 1/2 a wavelength behind, is it constructive? Well, if you can imagine, here's a wave. And constructive interference would be if a second wave had the crests and the troughs all lined up. Well, here's your one wave. If a second wave is exactly 1/2 a wave behind, so if it's going to start here, 1/2 a wavelength behind, it's going to look like this. And again, it looks like it's going to be destructive interference because you have the crest lining up with the trough of that guy. However, if you remember, when you go from over here we have air into soap, if you go into a more dense medium, what happens? Well, when it's reflected off a more dense medium, that wave gets inverted. So if the red wave, the original wave was like this, but now it's inverted, it's going to go like this and exactly line up with my black one. Therefore, the crests line up together, and it becomes constructive interference. So if this distance, the thin film right here, happens to be 1/4 of a wavelength, by the time it goes here and back, you're a half a wavelength behind. Since the original wave was inverted, a half a wave back causes it to line up and constructively interfere. So whatever light would correspond to the thickness of 1/2 of a wavelength of that soap, that color will be constructively interfered with, and you would see that light. As you go further down this soap film, you get different places. The wavelength of different colors will be constructively interfered with, and that's why it's going to be red, and then yellow, and then orange, and then green. Because the thickness changes, therefore you're constructively interfering different wavelengths of light. That's what this thing says. Different colors have different wavelengths. Therefore, as it gets thicker, other colors are constructively interfered with. So the key thing, light wave hits the soap. When it reflects, instead of being one direction, it's actually inverted. So if the wave that comes back is a half a wavelength behind, it will actually be the same direction. They'll both be below the medium, or both above the center of axis. That is what causes thin film interference. As far as polarization of light goes, anytime light is reflected, it becomes polarized. And polarized simply means it vibrates in one plane of vibration. A Polaroid material, then, is something that contains long molecules that allow waves to pass through only in one direction and absorbs the rest. The one direction that we allow light to go through is called the polarizing axis. And a polarizing filter is some material that polarizes light. You want to kind of think of a polarizing filter maybe like a picket fence or the bars of a jail cell. If you have a picket fence or a jail cell and you send a wave on a rope horizontal, it's not going to be able to go through those bars. It's going to stop. If, however, you send the waves going vertically through there, they'll be able to continue on through. So it will stop all the waves going horizontal, but allow the waves going parallel or vertical through that. If you would take two polarizing filters, one that's polarizing this way and one that's polarizing this way, and put them over top of each other, what's going to happen is no light will go through, because the one on the left only allows the horizontal light to go through. The one on the right will only blocks the horizontal but allows vertical. Well, if it blocks horizontal, that means nothing is left to go through that, and it will appear dark. So we'll show you a couple of these filters in class along with some thin films. A couple websites here. This one kind of talks a little bit about polarization. We know right over here light goes in every possible direction. If we're talking about polarizing stuff, unpolarized light, you know, is horizontal or vertical, if we just simplify it a bit. A filter blocks everything except the vertical, so that would be the polarized light, only the vertical light going through that filter. Talked about the picket fence, you know, if it's parallel, it allows light to go through. If it's horizontal, it would block that vertical light. And this is kind of what happens I guess I don't have a picture of those. Oh, here we go. So you have two polarizing filters that are lined up with the axes parallel to each other. You see right through. If they're perpendicular, then it blocks out the light when they intersect. I just found this on Wikipedia on thin film interference. This is what you're looking for. You can see these different patterns. Notice you see blue, and then the purple, and then red, and orange, and yellow, and then it repeats itself. Again, what happens is when the light hits and reflects, when it goes into that film, if this part, this distance from here to here is 1/4 of a wavelength, by the time it comes back out, you'll be exactly a half a wavelength behind. So if this was going like so, so if the wave is going this way, and we'd continue on like so, this wave, when it continues on, should be down. But remember, when it reflects, this guy actually gets inverted, so it would look more like this, and therefore the bottom will line up with the bottom, top will line up with the top, and so on and so forth.